Hey y'all, welcome back. In this video, we're going to introduce the idea of standard deviation, which is an important measure of spread in statistics. Before we do that though, let's quickly recap what we learned yesterday on our first day of stats. Where we learned about histograms, which are a good way of representing certain kinds of data in statistics. Basically, you have your possible data values on the x-axis, you have frequencies on the y, and then you create a bunch of little columns, a bunch of bars, which represent how often you saw each particular data value in your data set. And then we also learned about central tendency, right? Which was a measure of central tendency is just a nice single number, which somehow in some way measures the average, whatever the average is of your data set. The three most common are mean, median, and mode. We discussed some of their properties yesterday. Okay, so today I want to talk about one more measurement which can summarize a data, kind of like central data set, kind of like central tendency can. That's going to be standard deviation as a measure of spread. So to set that up, let's actually look at a couple of histograms from your most recent homework assignment. Right? These are two histograms, right? We have, although I haven't listed them, we have each of these columns corresponds to a value. Imagine this is maybe 1, 2, 3, 4, 5, right? And then these heights correspond to frequency. So if this was a 1 right here, we didn't observe 1 very often, but we observed 1, 2, 3, 4. We observe 5 quite frequently, right? What I want you to do is on the form, look at these two histograms, which assume that they have the same x-axis and the same y-axis. Tell me, which one has the larger median, or are they the same? Tell me which one has the larger mean, or are those the same? Right? So report that on the form. These two have the same mean and they have the same median. How can we tell? Well, remember that if you have two histograms that are symmetric, that is, I can draw a line straight through the middle and they look the same on the left and the right, they're going to have the same median, and their mean and median are going to be in the same spot. So for this one, the mean and median is right in the middle. For this one, the mean and median are right in the middle, right? And the middle on both of these is the same, right? So although these histograms look quite different, they have the same mean and the same median, right? So what is actually different about these two histograms, right? They have the same central tendency. If we were to try to summarize what made them different, right, we notice that in the first histogram, a lot of the data is clustered around the mean and median in the middle, right? We have a bunch of data that's right in the middle, a bunch of 3s, 4s, 5s, and 6s. Whereas over here, we have very few 5s and 6s. We have a lot of 1s and a lot of 5, 6, 7, 8, 9, 10s. All right, so we see that there's kind of a more clumpiness around here, a lot more clumping in the middle, and a lot more spreading out of the data here. Right? Central tendency, therefore, can't capture everything about a set of data, right? Although it's accurately captured what the centrality of each of these histograms was, it didn't really give us any inclination about what the actual level of spread was. Is it really clumped together in the middle, or is it really spread out? Right? So our goal here with coming up with a measure of spread is to find another single number which can tell us how spread out our data is. Okay, so that's the quest we're going to go on. The way I'm going to lay this out is as follows. I'm going to kind of lay out a few candidates for you as to what our measure of spread could be, right? And then we're going to find some problems with each of them, okay? First one is the most straightforward, which is the range, something you might have learned about at some point in maybe a stats module you've had before. The range is just the distance from the smallest number to the largest number, right? So this has some problems though, right? It's very simple, but there's some issues. For instance, go back to the previous pair of histograms and then tell me which one had the larger range. So pause this video, go back to those histograms. Which one had the larger range, or were they the same range? Okay, if we go back to those pair of histograms, right? If I just go largest minus smallest, I'm gonna get, let's say this is 10 minus 1, I'll get 9. Right? 10 minus 1, 9, right? So the range here, although it is a kind of a measure of spread, it doesn't really distinguish between these two very different histograms. So leaves something to be desired, right, in terms of what we can, want in a measure of spread. Okay? So the range we're not going to use too often. Okay, well, let's rethink this, right? Maybe instead of just subtracting the largest from the smallest, let's go more directly at what we were observing before, right? If we looked at our two histograms here, what we noted was that the data was very clumped around the middle here versus not clumped around the middle, right? So maybe instead of just going biggest minus smallest, let's try to think of how far is this data, how far are the data points from the middle on average, right? And let's make that more precise. How far on average are these data points from the mean, right? If based on our intuitions, we would expect that if we come up with some measure for that, we would expect this measure of spread to be small for this one because the average distance of our data points from the middle is not very large, right? It's quite clumped around here. Whereas over here, our data is very spread out here and a lot over here, right? So we'd expect a very large measure of spread for this one. So let's workshop that. And let's actually use some concrete data here. Let's say that you ask some friends how many movies they watched last month. You get 3, 4, 4, 6, 9, 10. Right? If we're trying to measure how far this data is from the mean on average, we should probably first figure out what the mean is, right? So mean here is just going to be add them all up, divide by 6. The mean of this data set is 6 movies. So on average, your friends are watching 6 movies a month. Right? Now let's think about how far each of our data points is from the mean. Right? I want to make a little table here. Right? So I've listed out all of our data points, 3 movies, 4 movies, 4 movies, 6 movies, and so on. And I've just copied the mean down for each time I write a data point. What I want to know is how far each of these data points are from the mean, right? So to do that, I'm just going to create a new column, and I'm just going to subtract across. I have my friend who watches 3 movies in a month. On average, my friends watch 6 movies, so this person is 3 below the average, right? So I'll give them a -3, 3 minus 6. Same thing for the next one, 4 minus 6, -2. And so on, right? So now I have a list of differences between the data points and the mean, right? Basically telling me how far away each of these data points is from the mean, right? Seems reasonable. So how can I find the average distance of my data points from the mean, right? Well, I found all of their differences. Let's just average them, right? Let's just take the average of all of those distances we just found in the last column. So go ahead and try that. Go ahead and on the form, calculate the mean of this last column on the previous table, right? Put your answer on the form. Your answer might surprise you here, right? So find the average of these guys. Okay, and what you're going to find, right, is if you take the -3 plus -2 plus -2 plus 0 plus 3 plus 4, right, all of those added together divided by 6, right, the number we had, the average distance is 0 divided by 6 equals 0, right? That's kind of weird, right? So this measure of spread that we were just constructing just gave us 0. It said that there's 0 spread. Ugh, that's not great, right? It turns out that this is a unique property of the mean. If you take every data point and then figure out how far that data point is from the mean and add all those differences up, you're always going to get 0. Right? Which is kind of cool and interesting, but it's bad news for us. It's not good if I'm looking at a bunch of different histograms that look spread out in different ways, and for each of them I say, oh, look, the spread is 0. Oh, look, the spread is 0. Oh, look, the spread is 0. That's not a very good measure of spread. Right? So let's keep workshopping this, and let's in particular look at what went wrong on that example. Right? So I've made a little number line here. Our mean was 6, right? And I'm going to make a little X for each of our data points. We had a 3, a couple 4s, 6, 9, the 10. Right? I lined these X's up as best I could on here. Okay? So what we did was we took each of these data points and we measured how far it was from 6, the mean. Right? This one was 3 below. Both of these were 2 below. This one was right on, so it's 0 below or above. This one was 3 above. This one was 4 above. Okay, so what happened here was we actually added all these differences together, but what happened then was this 3, positive 3, canceled this negative 3, and this 4 canceled these 2 negative 2s, right? That's kind of a feel bad, right? We don't, when we look at these data points some way over here and some way over here, if we're looking for average spread, it kind of feels weird to have these numbers way over here cancel these way over here, right? They should both be rather contributing to our spread rather than canceling each other out, okay? So the fundamental issue here is that the negatives are fighting, the negative distances are fighting the positive distances. That's no good. So there's 2 possible fixes to this. One is we can just take the absolute value for each of these distances. That is, instead of adding -3 plus -2 plus -2 plus 4 plus 3, we add 3 plus 2 plus 2 plus 4 plus 3, right? And then we could add all those, right, and divide by how many we had. That actually is an established measure of spread. It's called the average absolute deviation or the mean absolute deviation. Right? You don't need to know this for the exam. It's not a very often used measure of spread for mostly one kind of weird reason, and that is that there's a lot of calculus that goes on behind the scenes in statistics. And if you've had calculus before, you should know that calculus really likes looking at very smooth functions, right? And absolute value functions have what's called a kink, right? They go boom, boom, right? They have a very sharp turn, and those are not differentiable at those points, right? So calculus does not like this method purely because it doesn't like absolute values. So we actually have to go with a bit of a workaround here, right? The workaround here is we're going to actually square these distances, right? And that's going to lead us to standard deviation. So let's go back to the table we had before, right? This is how we've constructed it so far. I'm going to make one more column, and that is I'm going to square each of these distances. So -3 below the mean, that becomes a distance of 9 from the mean, right? Same thing here for -2 squared is 4, -2 squared is 4, 0 squared is 0, and so on, right? So now I have all positive numbers, right? So the negatives are no longer fighting the positives, right? And also squaring numbers is not something calculus has an issue with, right? So we're in the clear with calculus. If I add all these up, right, that's 42. And then if I divide by 6, which was the number I had, that means that the average of all these squared distances is 7. Remember, if I took the average of all of these, I got 0. But once I square each of them and add them up and divide by how many I had, the average of these squared distances is 7. Okay? This is another measure of spread. It's called the variance, right? So variance is basically the average of these numbers here. Add them all up and divide by how many you have. Okay? There's one more step. Remember that our data represents number of movies watched in the last month. Okay? What are the units on the 7 that we just calculated? Right? Let's actually go back. Right? So on these data points, this was 3 movies, 4 movies, 4 movies, 6 movies, and so on. Right? This was 6 movies, 6 movies, 6 movies, so on. Right? This was, if I subtract 6 movies from 3 movies, that's -3 movies. Right? So units here are movies, movies, movies. What happens when I square -3 movies? I get 9 squared movies. This is 4 squared movies, 4 squared movies. If I add all these up, this is going to be 42 squared movies, or movie squared, you could say, right? So, and then when I divide by 6, that's 7 squared movies, right? That just doesn't mean anything to anyone, right? If I say, oh, the average spread of the movies my friends watch, that's 7 squared, that's 7 movies squared, right? I already have enough trouble trying to conceptualize inches squared. What does movie squared mean? Like nothing, right? So the last step here, right, is we're going to take the square root. So this is why the variance isn't used as much as standard deviation, which we're about to define in a second, because these units are kind of funky, right? The variance is hard to deal with. So final step, we're going to take the square root of that number, right? This is going to fix our units, right? So we had 7 movies squared, right, for our variance. We just need to take the square root, and that gets us 2.65 movies as our standard deviation, okay? You could think of this as how, basically, what is the average number of movies away from the mean that each of your friends falls, right? On average, your friends are 2.65 away from the movies away from the mean, right? It's kind of an average measure of how far your data points are from the mean. We'll practice this in class, kind of what this intuitive notion means in class next time. Okay? But first, let's do one more practice, right? So to calculate the standard deviation of a bunch of numbers, what you're going to do is fill in the table on the following page. Okay? Basically, you're going to fill out your data points, find the mean of those, and copy that down as many times as you need. Take each of these numbers minus each other, so this number minus this number is this number. Square each of these to get the square distance from the mean. Add all those up. Right? Divide by the number of data points you had. And then take the square root. So let's go ahead and practice that. Let's say that you take a survey of your friends' heights in inches. Calculate the standard deviation of their heights using the table template on the previous slide, right? So go ahead and pause the video, use these 6 data points, right? And use this table here to find out what their standard deviation is. Okay, let's have a look at this, right? First step is always pretty easy. You're just going to copy all of those data points into the first column. Doesn't really matter what order you go in, right? Just get them all in there. Then calculate the mean. If I add all of these guys up and divide by 6, I should get 64. So copy that over and over and over into this column. Now we're going to find all of the distances of these data points from the mean. So 64 minus 64 is 0. 67 minus 64 is 3, and so on. Then, because we don't want the negatives to fight the positives, we're going to get rid of the negatives by squaring each of these, right? So 0 squared is 0, 3 squared is 9, negative 4 squared is 16, and so on. Okay, next we want to find the sum these up, right? What's the total of all these squared distances? Should be 58. If I divide by the number of data points I had, should give me, so divide all 58 by 6, right? So divide box E here, divide by 6. Should get me 9.67 inches squared, right? That's the variance. And again, that's not going to be what we want to stay with usually, because that's going to be the square units, which are hard to interpret. Right? And then we have our standard deviation is the square root of that, 3.11 inches, right? So you could say one way of kind of summarizing this data you have is that the mean height of your friends is 64 inches with a standard deviation of 3.11 inches, right? So on average, there's 64 inches, right? Give or take 3.11 inches on average, right? You would not be surprised to find that one of your friends was, say, around 3 inches shorter than 64. Right? We'll talk more about the intuitive notions about this next time, but thanks for watching this little bit long video, and I will see y'all next time.